discuss the topic MongoDB Web Performance Optimization metrics that actually matter. In this webinar, I will cover the concepts like why troubleshooting is hard, MongoDB performance architecture, about the investigation workflow, and different metrics, query metrics, CPU metrics, memory metrics, storage, replication, connection metrics, sharding metrics, and the case study of production scenarios and optimization checklist, and some of the important commands and key takeaways. MongoDB is widely used for the modern applications because it provides flexibility, scalability, and high availability. But as the application traffic grows and the data volume increases, maintaining the reliable database performance becomes increasingly challenging. The production issues can appear in different forms, like this. Here we can see slow response, application response time, increased query latency, high CPU utilization, storage bottlenecks, replication lag, connection spikes. And one mistake we all do is that we assume that a single metric will tell the story. But in reality, MongoDB performance issues are rarely caused by the single metric. So consider a production scenario, for example, when an application team or the users reports that the application responses time has significantly increased from a few milliseconds to nearly 4 seconds, then we DBS check for the MongoDB cluster health and observes that the CPU utilization is normal, memory usage is stable, and the replication is also healthy. At first glance, nothing appears wrong, but when we execute the execution plan, query execution plan, then we discovers that a frequently accessed query is performing the cold scan. Means it is examining 8 lakhs documents, but it is returning only 50 results because an appropriate index is missing. So there we can see that infrastructure was healthy, but the query was not. This illustrates an important principle that MongoDB performance optimization is not only about collecting every available metric, but it is about to identify the metric which explains why MongoDB is behaving this way. And we DBAs should follow a structured workflow for this. We have to understand the problem and identify the user impact, and we have to collect the relevant metrics and sorry, first we have to identify the affected layer where the issue originates, and then we have to collect the relevant metrics and correlate all the metrics to identify the actual real root cause, and then we have to implement the fix by targeted optimization techniques or strategies. Then we have to validate this improvement with the data. So rather than reacting to alerts, we have to correlate the metrics to identify the actual bottlenecks. Then before correlating the metrics, first we have to understand how MongoDB processes the request. So here we can see the MongoDB performance architecture. How here we can see different layers like application layer, connection layer, query engine layer, query planner layer, indexes layer, wire the tiger cache layer, storage engine layer, disk layer. So this every layer can have the influence on the application performance. Like first one is application layer. It will generate the database operations and poorly accessed patterns, and excessive request can overload this database. And connection layer, it will manages the client connections, connection leakage. Whenever there is connection leakages or incorrectly configured connection pool, it will consume unnecessary resources. Next, query engine layer and query planner layer. These layers determines how the queries are executed and whether the indexes are used efficiently or not. Next, index layer. In this layer, proper indexes will help the MongoDB to examine the documents which are required. Next, white tiger caching. Frequently accessed data will be stored in the white tiger cache in memory to minimize the disk reads. Next, storage engine layer. It will handle the persistent reads and writes. Like higher storage latency will affect the writes, queries, and replication. So in this way, understanding these layers will helps us DBAs to identify where the issue originates, where the performance issue originates, instead of collecting every available metric. Here we can learn about this performance investigation workflow. Whenever the users reports the application performance issues, then we should avoid collecting every available metric. Instead, we should follow a structured performance investigation workflow like this. um, Different steps we have to follow. Step one, we have understand the problem. So here we have to understand the problem and know the symptoms of the issues and identify when it started, who is affected, and also ask questions like why, which application feature is slow, or reads, writes, or both got affected, or is this issue happened after a new deployment, or is this issue happened to some users or every users. Like this we have to ask the question to define the problem. So defining the problem will narrow the investigation. Next, step two, identify the affected layer. So here in this step, we have to identify the affected database layer where the issue is occurring. So because different symptoms points to different parts of MongoDB. Like for example, we can see here different issues like slow queries, high CPU, slow rates, replication lag, connection errors. And the likely area we have to investigate is for slow queries, we have to investigate query plans and indexes. For high CPU issues, we have to investigate the expensive queries or aggregations. For slow writes issues, we have to check the storage or checkpoints. And for replication lag issues, we have to check disk or network or workload. And for connection errors issues, we have to check the connection management. So like this, we have to identify the affected layer uh, to know where the issue is actually occurring. So it will narrow the scope to the most likely area layer. And then step three, we have collect relevant metrics. Here we have to gather and collect relevant metrics and logs from the identified database layer, and use the baselines and trends for the comparison. And we have to focus on the metrics which reflects the symptom. Then in step four, finding the root cause. Here in this step, we have to correlate the metrics logs and identify the root cause behind this issue. And then if we have to validate that one root cause with the evidence. Next, in step 5, we have optimize and validate. We have to implement the fix by applying the different optimization techniques or strategies, and validate this improvement with the accurate data. Here from this we can understand different types of performance metrics. Like first of all, query performance metrics. Query performance is often the first place we have to investigate, because inefficient queries will affect the CPU, storage, and memory simultaneously. And here the important command for the query analysis is db.collection explain execution stat. And this command will shows the output like the important query metrics like execution time millis, total docs examined, total keys examined, and end returned. Here, execution time millis means how long a query takes to execute. Whenever there is a higher execution time, it indicates that there will be any missing indexes or large document scans or inefficient execution plans. This will increase the execution time. Next, total key. Here, the total keys examined means here, it represents how many index entries MongoDB must examine, and a higher value of this when compared to the total number of documents returned will indicates that there is an inefficient index design. And then we will see about the total docs examined versus end returned. Um, this comparison will reveals the query efficiency. And here, for example, we will consider one production scenario. Like if the index is not existed, then MongoDB scans the full collection. Like for example, it scans 8 lakhs documents, but it returns only 50 documents as results. So there will be the difference between this total docs examined versus and returned. So we have to optimize this issue by creating an index so that MongoDB scans only the required documents related to that index. So if the query is efficient, then it should examine close to what they return. Means total docs examined versus n return will be close. And then cold scan versus xscan. The execution plan, like cold scan versus execution plan, will explains whether the MongoDB is performing the cold scan or xscan. A cold scan is nothing but, as I said earlier, MongoDB scans the full collection, and it will examines, like for example, it examines 8 lakhs documents but returns only 50 results. So because there is no appropriate index, so no appropriate index is missing. So we have to optimize this issue by creating an index by using the command create index, and then MongoDB scans the documents which are required documents only based on that index, and there will be documents examined will be 50 and the written documents will also be 50. So in this way we have to optimize this issue. So this winning plan, whether it is goal scan or is scan, it explains the performance behavior. So understanding the slow query matrix will tells us that the problem is existed, but like this execution statistics will tells why the problem is existed. Then CPU analysis, finding the real root cause. High CPU utilization is also one of the most common production alerts. But it always doesn't always means that MongoDB needs more CPU resources, because sometimes CPU is a symptom of an underlying problem. Like common CPU causes includes like any missing indexes causing cold scan, or expensive aggregations pipeline, and expensive queries and aggregation pipelines, and a high application concurrency in when there is an increased in query latency. Like this, there are different CPU causes, and also expensive aggregation cold scan. So as I said earlier, cold scan examines. Sorry, when a query executes the cold scan, so it will examines more number of documents but returns only fewer results. So this will result in higher CPU utilization and increased query latency, and additional disk reads. And another common CPU root cause is expensive aggregation pipelines. Means like operations such as lookup, group, like this, and multiple transformation stages. These will consume more CPU resources while processing the large data sets. For this, we have to use some optimization strategies, like filter the documents earlier using the match, and we have to create the indexes that can support the query filter, and reducing the unnecessary pipeline stages. These are some of the optimizing strategies for reducing this high CPU utilization. And here we can see the structured CPU investigation workflow. Whenever there is high CPU utilization, we DBAs have to check the running operations and identify the expensive queries, and analyze the explain plan, like whether it is performing cold scan, like that. And we have to then we have to review index usage, because if there is any indexes missing, like that we have to review, and then we have to optimize the query or workload. And here the important command we have to use for checking the running operations or current operations is db.current operation current op. It will shows the current operations which are in use, and also helps us to identify the long running queries, blocking operations, expensive aggregations. For example, if a query has been running for a long time, it means it indicates that there is an increased CPU utilization. So here we have to remember one thing, that adding more CPU resources will reduce the symptoms temporarily, but reducing the inefficient queries or optimizing those inefficient queries will addresses the real root cause behind the performance issues. White tiger cache and memory behavior performance metrics. MongoDB uses this wide tiger cache, which heavily relies on the memory to improve the performance. Frequent, as I said earlier, it stores the frequently accessed data in memory, which allows the MongoDB to read from the memory rather than repeatedly reading from the disk. So here the important thing is that goal is that we have that the working set should fit in the application working set should fits in the cache. Working set is nothing but the data which is frequently used by the application. So if the working set fits in the cache, then it will read from the memory. So thereby there will be faster queries and there will be faster responses to the users. And if the working set is not is exceeding the cache, then there will be more disk reads. It reads from the disk, so there will be more disk reads, and there will be higher latency, and thereby it results in slower application responses to the users. And here the important command we have to use for the cache analysis is that db.serverStatus.cache. And here the important cache metrics or like white tiger metrics or cache usage, dirty cache, eviction activity, pages read into cache, pages written from cache. First of all, we will look one by one. First of all, cache usage is nothing but the amount of cache which is in use. And here there is one misconception that high cache usage means we need more MongoDB needs more memory, but it is not always true, because white tiger cache is designed to use the available cache efficiently. But but this cache pressure will becomes a concern when pages are frequently read from the disk, when the working set doesn't fits in the cache, and when there is increase in the poorly accessed query patterns, and eviction activity increases significantly. In those cases, cache pressure will becomes a concern for us. Then dirty caching. Dirty caching means the modified data that has not yet been written to the disk. So whenever there is heavy write workloads, during those heavy write workloads, there will be heavy writes and the dirty cache will grows, and there will be checkpoint process runs at regular intervals. These checkpoints will flushes these dirty cache pages from this temporary memory to the permanent storage to ensure that the data is durable. And then a, a high dirty cache percentage is not actually automatically a problem, but if it combines with storage or any frequent checkpoints, it will increase or affect the right performance. Then eviction activity. Whenever the cache becomes full, then wider tiger cache removes the older pages to make a room for the newer ones. This process is called eviction activity. Higher eviction activity indicates that there is a cache pressure and missing indices causing unnecessary reads and large working data sets. Due to that, eviction activity will be increased. Next, pages read into cache. It is nothing but the data loaded from the disk. And pages written from cache, it is nothing but data that flushed to the storage. And here we have to remember that instead of adding memory, we have to question ourselves like why cache is under pressure. Is cache is responsible for the performance issue? Cache pressure is responsible for the performance issue. Like that, we have to check the cache pressure. Next, disk input output performance metrics or storage metrics. Storage metrics can have the direct impact on the application responsiveness. So because even if a query is well optimized, um, if the storage if the storage subsystem cannot keep up with the workload, then it will causes different performance issues. So here we can see the important storage metrics like read latency, write latency, input output operations per second, disk throughput, queue length. And the important symptoms for this storage bottlenecks or slow writes, increased query latency, replication lag, and delayed checkpoints. And for those symptoms, the optimization strategies we have to use the SSD or faster SSD or NVMe storage, and we have to monitor the latency trends over that time, and we have to reduce the unnecessary write operations, and optimizing the application workload patterns, so that there will be no replication lag. Like that, we have to use some of these optimization strategies to reduce any storage issues, storage performance issues. So here we can see this we have to know that storage metrics should always be interpreted alongside the cache and the query metrics, because for example, high disk latency may be caused by the cache pressure or the inefficient queries rather than the storage hardware issues. So we have to interpret those storage metrics along with cache and query metrics. Next, replication performance metrics. Here, replication is nothing but maintaining the data copies across multiple servers. So it will provide the high availability. So, but poor application performance can affect this both availability and the application responsiveness also. And here, the important replication metrics are like replica set health, replication lag, oplog window, flow control. And coming to replica set health, VDBA should all regularly check the replica set status health using the rs.status command. And then we have using this command, we also have to check for primary and secondary member health, replica state, election events, and replication progress. How is it happening? And then replication lag. Replication lag is nothing but how far a secondary is behind the primary server. So here the important useful command is rs.print secondary replication info. By using this command, we can see the output like 2 seconds behind the primary server, like that. It will show the replication lag. Whenever there is high replication lag, it will be caused by slow storage on secondaries, when there is network latency, and during the heavy write workloads, and when there is resource limitations, we can see the replication lag or replication lag will increases in those cases. And then oplog window. Here, the MongoDB stores the replication operations in this oplog. Um, the important command to view this oplog information is db.getReplicationInfo. By this command, we can view the oplog information, like it will show the output like oplog size, log size, like that. And this oplog window represents how long the replication history is retained. Whenever there is a small oplog window, it will increases the risk that the secondary server falling behind the primary will request full resynchronization instead of catching up from the oplog. So monitoring oplog size is very important during the heavy write workloads activity during those periods or maintenance, like this. Next, flow control. MongoDB uses this flow controller to prevent the secondary servers falling too far behind the server. So whenever the secondaries cannot keep up with the primary servers, then this flow control, when we activate this flow control, it temporarily slows the writes on primary. Here we can see that workflow. During heavy write workloads, automatically there will be increase in replication lag. So the secondary server falls behind the primary, too far behind the primary server. Whenever this we activate, like MongoDB activates this flow control, then it will slows the writes on the primary server, to reduce that replication lag between the servers. Next, connection and workload metrics. Connection metrics are also one of the most common causes for the MongoDB performance issues. Even a well-optimized query becomes becomes slow, or if the connections, if there is any poor connection management, it will causes some different issues, connection issues, like we can see here the different connection issues like connection leaks, extensive connection creation, incorrectly configured connection pool, and sudden traffic spikes. And here we can see the important command to know this connection metrics is that db.serverstatus.connections. This command will displace the current connections, available connections, and the connection growth trends. so that we know about what are the connections currently running, available connections like that. Also, in addition to these connection metrics, we have to check the workload metrics like insert, updates, delete, query operations, because sometimes the performance issues can be caused by more application workload rather than any connection issues. Next, another metrics, MongoDB sharding performance metrics. Like sharding, here the sharding enables the MongoDB to scale to scale horizontally to distribute the data between among the different shards. So the sharding will provides the high availability and high scalability. And here the different sharding performance metrics like oh sorry, even sharding provides higher scalability, but it also causes some of the performance considerations or any issues. It means it has advantages, but also due to that there will be some issues also, like hot shots, chunk imbalance, balancer activity, jumbo chunks. Like first of all, hot shots occurs when one shot receives more traffic than the others. Like it will shows like symptoms like higher CPU utilization, increased query latency, and there will be uneven storage growth. These are some of the symptoms it will show. And here the important cause for this is inappropriate shard key, which is concentrating the data or workload only on a single shard. So that's why hot shards occurs. Next, chunk imbalance. MongoDB distributes the data by using chunks. If the chunks are unevenly distributed, then one shard receives more data than the other. This will result in chunk imbalance and unnecessary resource utilizations. Then balancer activity. MongoDB moves chunks between the shard to maintain the data properly balanced between the shards. Whenever there is a frequent balancer activity, it will be caused or indicates there is a rapid data growth, uneven data workload distribution, or else is there any poor shard case selection like that. And so since this balancer activity will consume the CPU resources and disk resources, so we have to investigate excessive, if there is any excessive balancing, we have to investigate that, because it will causes performance issues. Next, jumbo chunks. Jumbo chunk is nothing but a chunk that cannot be split. This So it will prevent the MongoDB to maintain the data balanced between the balance among the shards. So the possible causes will be, there will be insufficient splits, large document scans, and the poor shortcake distribution. And the possible impact will be, there will be reduced scalability and uneven shard utilization. Then one important skill we DBAs should have is that we have to correlate the metrics rather than relying on a single metric to find out the real root cause. Like here we can see one production scenario example. Whenever we observe like CPU utilization is high, execution time is high, total docs examined very high, disk read latency high, replication lag normal. At first, when we observe these values, these things, we think like that, that there is high CPU utilization, so we need more CPU resources. But it is not always true, because after executing the query execution plan, as we said earlier, like using execution stats command, then we can see that a frequently accessed query is performing cold scan, means examining more documents, but it giving fewer results because appropriate index is missing. So this will shows that the relationship between these metrics like will become clear after that. So here we can see that whenever, so there is missing index, So it will result in collection scan. So it is so millions of documents are reading from the memory, and there will be so it will result in high CPU utilization. Thereby, there will be more disk reads, and it will give the slower application response to the users. Like this, we have to correlate all the metrics to find out the what's the real root cause, rather than on a single relying on a single metric. So the same approach will be used for any replication lag. Like that, we have to correlate the metrics to find out the real root cause. So this illustrates an important principle that individual metrics shows the symptoms, but correlating the metrics reveals the real root cause. Then the important commands for troubleshooting any MongoDB performance issues, like that here we can see. First of all, db.server status. This command is used to check the server health. And when we put like db.server status dot cache, we can that command is used for cache analysis. When we use db.server status dot connections, we can see the current connections, available connection, like connection statistics we can see. And then db.current operations command. This command will display the current operations in use, and also helps us identify any slow running queries, blocking operations, expensive aggregations. And explain execution stat command. This command is used for analyzing execution plans, and it will show the output, like as I said earlier, execution time millis, total docs examined, total keys examined, in return it will show the output like that. And then next command, rs dot status. This command is used to check the replica set health. And then rs dot print secondary replication info command. This command is used to review the replication lag, and by this command it will shows the output like 20 seconds or 2 seconds behind the primary server. Like that, we will see the output. And db.get replication info command. This command is used to view the oplog information, like it will shows the output like oplog size, log size, like that. And then db.collection.get indexes command. This command is used to review the existing indexes. So these commands are important, and these are solid starting point for investigating the MongoDB performance issues. Then MongoDB performance optimization checklist. When troubleshooting these MongoDB performance issues, we have to review the following areas. Like in query performance area, we have metrics. We have to check or review slow queries, execution plans, cold scan versus six scan, index effectiveness, aggregation efficiency. And in wide tiger cache metrics, we have to check cache usage, dirty cache, eviction activity, cache pressure. And in storage metrics, we have to check read latency, write latency, IOP, input output operations per second, checkpoint performance. And in replication metrics, we have to check the replication lag, oplog window, flow control, replica health. And in connections or operations metrics, we have to check the current connections or operations and connection utilization and workload changes. And in shorting metrics, we have to check hot shots, chunk distribution, balancer activity, jumbo chunks, like that. So we have to monitor these areas or metrics continuously and analyze the trends, and optimize if any issues, and thereby we have to improve the performance, MongoDB performance. Key takeaways. So from this webinar session, we understood that MongoDB performance optimization is not only about collecting every available metric, but it is about understanding the relationship between all the metrics. Like for example, high CPU utilization may be caused by the inefficient queries, and high disk latency may be caused by the cache pressure or storage metrics, and replication lag may be caused by disk or workloads, and connection issues may appear as the MongoDB performance problems. So, so we have to follow a structured workflow. like this we can see here. We have to understand and identify the user impact and identify the affected layer from where the issue is originating, and then we have to collect all the relevant metrics related to those symptoms, and then we have to correlate those metrics to identify the real root cause behind the issue, and then we have to optimize that by implementing the fix, and then validate the improvement with the data or evidences. So final thoughts like so successful MongoDB performance optimization doesn't always rely on the dashboards or alerts, but rather than that, we have to understand the MongoDB internals and metrics, and using those metrics to answer question like why is MongoDB behaving this way and what action should be taken. So by focusing on all these metrics, we DBS can troubleshoot the issues faster and will maintain a reliable MongoDB environments that can scale up with the growing workloads. Thank you. Thank you for joining this session.